And uh, it is our fortune to have a personality of your stature today to interact with our students. I always say the students are very bright, but they're very fortunate today to get this opportunity to interact with you. Uh, we will start in 2 minutes, right, Dr. Sanobar?
Noted, ma'am. Yes, we are all set, almost all set, ma'am. A few students are yet to join us. I'll begin in 2 minutes, ma'am. If that's okay.
The weather is really cold here. We had seen a lot of snowfall last week, so
Okay.
students.
So it's a
Yeah,
winter, right? In your
yes, extreme winter, and the
okay.
transport is affected. So these students are supposed to be seated by 9:30, but because of all
Oh,
transport issues and other issues. But
it's
I'm
okay.
really
Yeah.
sorry for this inconvenience.
Oh, that's good. I mean, still many students. Yeah, glad to see many students. Yeah, it's a good.
They were very excited when we announced your lecture.
Thank you.
Very
Thank you.
thrilled.
I request the faculty members to please help me get the students seated quickly so that we can start the event. Students, please take your seats very quickly so that we can start the event. Our guest is waiting. All students are requested to be seated and keep their mobile phones on silent mode throughout the event. Students, settle down quickly. We're waiting for you all so that we can start the event. Our guest is already connected online with us. Students, settle down quickly. You may occupy the front rows, please. I request the dear colleagues to help me make them settle down so that we can start the event. Good morning.
Dr. Sanobar, we can start now. Actually, Professor Peter, we asked students to register, and the registrations were very large in number. So
Okay. Yeah.
it's good to see such an excitement among students. They're actually very thrilled.
Yeah.
Yes, ma'am.
In
Actually, it's a
particularly
big
for
crowd.
the really bad weather.
Got a little delayed. We're really sorry about the delay, sir.
No
Dr.
problem. No
Sanobar, please
problem.
start.
Yeah.
We live now.
Thank you, ma'am. A very good morning to one and all present today. I, Dr. Sanobar Khan, Associate Professor at Amity University, Tashkent, welcome you all to this event. Amity University Tashkent has been organizing international guest lecture series in its yet another move towards holistic development of its students. The university has initiated monthly lecture series, an experience sharing session by the eminent personalities from industry, research, and academia. The lecture series provides a platform for our students to interact with great minds and get inspired by their success stories. It aims at encouraging international and interdisciplinary communication and collaboration, discussing the trends and latest topics around the globe, increasing their broader impact to shape the career of our undergraduate students. I am privileged to share with you, dear students, that the first talk for spring semester 2023-24 in the International Guest Lecture Series is to be delivered by none other than a highly eminent academician in the field of education and a world-class scientist, Professor Peter Hang-Ju Chong, Associate Head of School Research at the School of Engineering, Computer and Mathematical Sciences, Auckland University of Technology, New Zealand. Can we put our hands together and welcome him very warmly?
Thank you.
Thank you. The topic of discussion for the day is a joint physical layer network coding-based medium access control. Indeed, a much desired topic of discussion in the world of information technology for encouraging young minds of tomorrow. We are highly grateful to Professor Dr. Gurinder Singh, Group Vice Chancellor, Amity Universities, for encouraging us towards such activities. I, on behalf of the entire Amity family, thank for the blessings of Mr. Amol Chauhan, Trustee, Amity Education Group, for encouraging us to be reaching out to our students in various innovative ways. I thank our director, Mr. Babur, a dynamic, humble, and innovative leader who reaches out to the students through various activities of their interest time and again. I sincerely thank our first Deputy Director, Amity University Tashkent, Dr. Naina Chaudhary, for encouraging our students to gain maximum out of activities at the university. Ma'am has her expertise in accreditation and ranking and international affairs. She has handled the university accreditations like WAS, NAC, and quality review by QAA. Ma'am, on behalf of Amity family, I invite you over to the platform for welcoming our speaker for the day, Professor Peter Hang-Ju Chong. Thank you, ma'am.
Thank you. Thank you. Yeah,
Thank you,
thanks a lot.
Dr. I will
Okay.
not take much of the time because it is the time that we should hear Professor Peter. But
Okay.
I always say that the students of Uzbekistan are very, very bright. But I will again repeat that they're very, very fortunate to get this opportunity to interact with the professor of your stature. I'm sure they'll have a lot of takeaways from the lecture today. So I'll quickly hand it over to you, sir. I'll not take much of your time, but it is a pleasure. And on behalf of the whole university, I welcome you once again. Welcome to Amity Tashkent. Thank you.
Thank you. Thank you.
Thank you so much, ma'am, and welcome, sir.
Okay. Yeah. So I think, yeah.
Let us take the event forward, and without any delay, I would like to introduce the guest for the day with his kind permission. May I, sir?
Yes, please.
Thank you. Thank you. Professor Peter Hang-Ju Chong is the Associate Head of School Research at the School of Engineering, Computer and Mathematical Sciences, Auckland University of Technology, New Zealand. Between 2016 and 2021, he was the head of Department of Electrical and Electronic Engineering at Auckland University of Technology, New Zealand. He received his bachelor's in electrical engineering from the Technical University of Nova Scotia, Canada in 1993. He pursued his PhD degree in electrical and computer engineering from the University of British Columbia, Canada in 2000. Sir is currently also an adjunct professor at the Department of Information Engineering, Chinese University of Hong Kong. He is an honorary professor at Amity University, India. He is a fellow of the Institute of Engineering and Technology, UK. Professor Chong is listed in the world's top 2% scientists, published by Stanford University in 2022. Professor Chong received the Research Excellence Award from the Faculty of Design and Creative Technologies in 2023. His current research projects focus on machine learning techniques applied to software-defined vehicular networks. Sir has been developing techniques for deep reinforcement learning, based resource management for future 5G V2X networks. His research interests mainly lie in the areas of wireless mobile communication systems, including radio resource management, multiple access, mobile ad hoc network, vehicular ad hoc networks, green radio networks, and 5G V2X networks. Sir has published his research work in over 300 journals of repute. Sir has edited 2 books and 13 book chapters in the recent past in his area of research. Without much ado, I invite our speaker for the day over to the dais. Over to you, sir. Thank you.
Thank you. Thank you. Thanks so much for the
Put your hands
chair.
together and welcome the guest for the day.
Thank you. Thank you. Yeah, thanks a lot for the chair, for your patience to introduce me. Next time I need to shorten my bio. It's a bit too long. Okay, anyway, thank you so much. And also I think
Couldn't
this is my...
add every achievement of yours, but nevertheless, there are many more hats to be added to your profile. Thank you for joining us.
So yeah, I think this is my second time to give a lecture to your university, and I'm happy since I'm also an honorary professor for Amity University. So I'm happy to support all the academic activity for the Amity University. So I'm very glad to see many students. It's very good, you know, whenever you give a talk, you have many students to attend. Hopefully at the end, as the chair mentioned, some of you will be able to pick up some knowledge or information from me. Okay, so let me share my slide first. Yeah. Okay, let me see. Maybe this one. Okay, can you see my slide? It's okay?
Yes, yes, Professor Peter.
Okay, good. Okay. Okay, so yeah, I think let me start. So I think good morning. For my time actually is okay, let me see how come the screen. Okay, let me reconnect the screen. Okay.
So it's visible to us, but you could
Okay,
make it
right?
screen maybe.
Yeah, okay. I think somehow I have 2 monitors. So okay, that's okay. Maybe I just using this mode.
Visible
Yeah,
to us, sir.
okay, good. Using this mode. Okay, so let me good morning. Here is at 6 p.m. So I think the timing is good for me. So as mentioned, my topic is a joint physical layer network coding based map for vehicular ad hoc networks. I am Peter Chong. So I think I gave a talk last year. I'm not sure how many of you have attended my talk, but I think it's a good opportunity for me to introduce my university to you. So I spend few minutes, you know, give a briefing. So this is me. So I received my study or my degree from Canada. Now, before that, actually, I'm now in New Zealand as a professor at AUT. So before that, I also have worked in number of places like Singapore, Finland, and Canada. So as I mentioned, I'm also a adjunct professor and non-professor in other university. Okay, so I think first of all, you know where I'm coming from. I'm coming from Auckland. So again, that's quite far away. If you look at the map, actually it's really, really far. So I checked that there's no direct flight that can fly so far from my Auckland to your city, Tanskan. So I think one way is to need to transit. So if you look at the hour, actually that may cost take 24 hours from here to reach to your city. So I think nowadays the technology is very good. In particular, this online meeting that can give me opportunity to give a talk to you. Okay, so this is the New Zealand. I believe not many of you have been New Zealand because so far from everywhere, but that is actually quite well known. So I think one of them in terms of is the fruit. Kiwi is our a major fruit, and also another is the lamb here. New Zealand has about 5 million population, but we are almost over 20 million lambs here. So that's why I can see actually that is the fact that we have more lambs than human in New Zealand. Another thing is very well known, honey. Another that is definitely, I believe that many of you have seen the movie Hobbiton or the Lost of the Ring. Actually, the director is from New Zealand, and most of the scene actually are filmed in New Zealand as well. Okay. So this is New Zealand, right? I mean, it's not big, but it's quite a reasonable size. So our size, if you look at this compared to Japan, we may be about 2/3 of the size of Japan, but in terms of population, we are much less. Our country has only about 5 million population, but in Japan, there's a 125 million. So you can see actually it's really sparse here. The density is very low. So I'm not sure if you know the city, the capital of New Zealand. Many of you may have heard Auckland, but you may not know the capital. The capital of New Zealand actually is not Auckland, it's Wellington. But Auckland is the largest city in New Zealand. 1/3 of the population actually are living in Auckland. So even though we have only 5 million population, but we do have many universities, very good education here. We have 8 universities in New Zealand. One of them is AUT, my university. And the oldest one is called University of Otago. I'm not sure how many of you of this university you have heard before. So AUT actually is a new university starting from year of 2000, but we are not new in terms of history. Back then, more than 100 years ago, we already started our education called as a Auckland Technical School. From 2000, we are upgraded to become a university from a polytechnic, and we are the only one in New Zealand to become university from polytechnic. And our major campus is at the Auckland City. So we are the youngest of eight New Zealand university, but our history has over 110 years old. We are actually the second largest and fast growing university in New Zealand right now. We have 4 campuses. We have over 27,000 students with over 2,000 academic staff. So even though we are new just from 2000 to become university, but in terms of the academic performance, we're doing quite well for the past several years. This year, from Times, we ran top 500, top 1%, and some other category, we also ran very well. So AUT has 5 faculty. We do not have medicine. We don't have any other pharmacy, but we have a law and some health science. My School of Engineering, Computer and Mathematical Science is one of the schools under Faculty of Design and Creative Technology. So our school has 4 departments: computer, electrical, mathematical, and mechanical. Our school is quite big, as about over 100 academic staff, and we have over 3,000 students under our school. Our school also is doing quite well in terms of this academic performance. From last year QS ranking, a few of our subjects are ranked from the QS. Okay, so this is our campus. As usual, is a quite modern campus and it's quite new. So hopefully some of the, so there's some opportunity for your student or academic, to visit us in the future. Another thing, the scenery for New Zealand is quite beautiful. We have the lake and also many volcanoes, which are not live one, but you can visit them. Okay, so this is some overview about where I'm right now. So let me start the topic. So the topic is a joint physical layer network coding based medium access control for vehicular ad hoc networks. So what is the background? That topic actually is related to the transportation, to the driving. As you know, right now, the traffic accident increasing a lot for the past many years, and that really caused a lot of casualty and property loss every year. In fact, most of these accidents are caused by the poor driving, improper behavior of the driver, and some of the hassle on the road. So in fact, many of these, complicated traffic situation, for example, intersection blind spot, in fact, many of them can be avoided to have the accident happen. So let me show you one accident happened in China in 2017. There's a real accident captured by the highway camera. Okay, I hope you can see it a bit small, right? As usual, many animals that can run around on the highway, like say, see the the lambs are running the highway. To them, they're very intelligent. They have no problem. But whenever accident happen, as usual, the driver would like to go out of the car, right, to negotiate or to argue. But that is very dangerous if you do that in the highway. You can see the truck coming. So I mean that accident really happened. I mean, in China, I think that is not that is also quite common in many countries as well. So in fact, many of these can be avoided to reduce the accident using the technology, what we call the vehicular network technology. So one of the technology that can help to reduce this kind of accident is called vehicular ad hoc network, or VNet. What is VNet? VNet basically is kind of communication network to allow vehicle-to-vehicle communication. So VNet has been proposed for quite some time to reduce the risk of road accident by providing some kind of safety-related service, let's say collision prevention, hazard warning, and so on. Now, VNet is based on the standard called V2X network standard. V2X stands for vehicle to anything communication network. And that V2X network can be based on two major standards. One of them is based on 5G cellular V2X. The other one is based on DSRC, dedicated short range communication. So V2X actually comprise both vehicle to vehicle communication and vehicle to infrastructure communication in order to meet the goal of VNet by broadcasting this real-time safety message among the cars. So let me give you a very brief overview about this V2X network, what it is. So in the V2X network, normally we need some hardware to support. One of them is called roadside unit. Those roadside units will be installed to some of the road infrastructure, for example, traffic light, lamppost. In order to allow you to communicate, you need another hardware called OBU, on-board unit. The on-board unit will be installed in the car that, to allow to have the V2X communication. So V2X communication support different kind of mode. One of them is called V2V communication, vehicle to vehicle communication. If two cars with the OBU, if they are close to each other, they are able to communicate to each other, means that they can send message to each other if they're close enough. However, in some situation, if the two cars are very too far from each other, they are not able to send the message to each other. In that case, in order for them to communicate, they have to rely on V2I communication, vehicle to infrastructure. For this example, the blue car can send a message to the roadside unit at the traffic light, and the traffic light will relay the message to the gray car. This is another example for V2I communication between the gray car and the school bus. Another communication is called V2P. P stands for pedestrian, vehicle to pedestrian communication. So nowadays, many of the smartphone has already this V2X chipset that allow you to communicate with the car. So For example, the bus and the pedestrian can be communicating. Sometimes that is very useful. For example, when the school children, when the kids are about to cross the zebra road, so before they cross the zebra road, their smartphone will be able to send a message to the incoming car. So those cars will be able to receive that message, and then in order to slow down or to stop in advance to let the kids to cross the zebra road. Okay, so some of the typical V2X safety application as usual, like the hazard warning. I know in particular in your country with the heavy snow, there's a lot of what we call the black ice. If those black ice can be identified in advance, so with this technology, this black ice message will be able to send to the driver in advance to know this dangerous situation. Another application can be used for collision prevention. For example, for the forward collision warning, right? As you know, that's typical that that the two-way car road, but if a car is blocked by a truck, so those they are not able to see each other. So that will be very dangerous for the car behind the truck try to take over the truck, you know, to pass the truck. Another is called the intersection collision warning. At this intersection, we call the blind spot. The car coming out from the intersection may not be able to see the car on the main road. So with this communication, they will know they can see each other by sending the message. Okay, so as I mentioned, V2X can be based on two standards. The study I try to introduce to you here is based on DSRC, so I will mainly focus on this one. DSRC stands for Dedicated Short Range Communication. So in the DSRC, every vehicle will be generate and broadcast this basic safety message we call BSM, and the BSM contains some essential information. For example, the location of the car, the speed of the car, and the moving direction of the car. So if the car are able to send this BSM message with the neighboring car, so they can maintain the neighborhood map in order to help the driver to know the driving situation, the traffic situation, in order to avoid the potential accident. So that is the overview of the DSRC. The DSRC protocol, if you're familiar with the wireless network protocol, like let's say Wi-Fi or the cellular, is very similar. So DSRC has 4 layers. The bottom layer is normally always the physical layer, and the physical layer used by the DSRC is based on OFDM scheme, orthogonal frequency division multiplexing, and the channel bandwidth is 10 megahertz, works at a 5.9 gigahertz. Above the physical layer is called the MAC layer. So the physical layer will be able to use 4 different modulation, BSK, QPSK, or 16 or 64 kAM, to allow you to send the data rate from 3 megabit per second to 27 megabit per second. Okay, so above the physical layer is the MAC layer. The MAC layer used in the DSRC is called IEEE 802.11p. I believe that IEEE 802.11 is unfamiliar to you because we are all using Wi-Fi. Our Wi-Fi all belong to the IEEE 802.11a, AC, or N standard. So that is actually you know already. But for the DSRC, it's also a family of the Wi-Fi under IEEE 802.11, but the standard 11p. So you can consider that IEEE 802.11p is some kind of the car, is a Wi-Fi for car. So it's a car Wi-Fi, you know, for simplicity. So that is the major MAC layer. So above the MAC layer, the other layer is 1609.4. That's another MAC sublayer. Is to look after the channel switching. Later, next time, we'll talk about the channel switching. And above that will be the upper layer, 1609.3 and then 1609.2 to look after the security and the network service. And this DSRC protocol, similar to the Wi-Fi, support the well-known IP Internet Protocol. For example, IPv4, IPv6, TCP, UDP as well. So the top layer will be the application layer. So one of the important layer is the upper MAC layer, IEEE 1609.4. That is to be responsible for the channel division and switching. So for the channel under DSLC, there's a 7 channel. Each channel has 10 megahertz of the bandwidth. And that among these 7 channels, the one in the middle is called common control channel, and the other is a share is a share channel. So that is the frequency domain. So for the time domain, each frame under DSLC is 100 millisecond. So for this 100 millisecond divided into 50 millisecond for the common control channel and the share channel. So every car will be synchronized to this time frame. So every car, if they want to send the safety message, all the car will be sending under this common control channel. If they want to send their own, let's say, non-safety message, they can send this to share channel. So the common control channel will be used by all the car share to send the safety message. So heavy collision will happen. And the share channel, the car can send the private message from car to car. Okay, so what is the problem of the existing DSLC? So that we like to do the research to improve the MAC layer. One of the problem is what we call the a typical problem for the IEEE Wi-Fi, which is the gray zone area, in that some car can detect to send a hello message, but the car are not able to receive the message from each other. That's a gray zone area. So as you can see for the CDF, actually the DSLC, due to this gray zone area, is not performing well. You can see 20% of the car received the very poor reception, less than 20% PDR. PDR stands for packet delivery ratio. And majority of the 65% of the car, they will receive the packet between 20 to 80%. So the packet delivery ratio under DSLC is not that great. Second, as you know, DSLC support different data rate, all the way from 3 megabit per second to 27 megabit per second. And the performance for different data rate actually, again, is very poor. So that's why it's very bad when you send the broadcast safety message if the reception is no good, because that is related to the safety. Okay, on the other hand, DSLC also not good performance in terms of the node density increase. You look at the graph here, N represent the number of vehicles in the network. As you increase the number of vehicles, the packet delivery ratio on the y-axis actually drop substantially. So that's why that is no good, with referring to the high number of vehicles in the network. Okay, so before I introduce our technique to you, so maybe I try to briefly to tell you what has been done in this area in terms of the MAC layer, medium access control. One of the technique is called the repetitive transmission. So the idea is very simple. The first one is called the synchronized fixed repetition. The idea is that, look at the diagram. Sender 1, you can consider as a vehicle number 1. Sender 2 can be the vehicle number 2. So what to do is that each car can repeat sending the same broadcast message over a certain period. So as you can see for the green sender 1 try to send the same BSM message repeatedly in multiple time slot, as well as the sender 2. So as you can see, they randomly send the same message over multiple time slot. So there's a possibility some of the BSM message sent by both sender 1, sender 2 may be collided, because it is, look at the first one, the green and blue, they send the BSM message at the same time slot, so they're collided. but that is fine because since they are sending so many of them, there's a possibility some of them are not collided. For example, look at the green sender 1. The second one, green, actually is not colliding with the blue, and similarly the blue, the sender 2 as well. So these two can be sent successfully to be received by other cars. So look at the performance. So as you can see, if you increase the number of transmission on the x-axis, all right, for sure, the probability of a failed reception decrease. Okay, but however, there's a trade-off. If you increasing, let's say, look at the figure on the left. If you're increasing the number of transmission, transmitting, then the probability of failed reception decrease. That is understood. However, when you keep increasing to many high number, then the chance for the probability of fail increasing, because if you are retransmitting too much, then the chance of the car to send the same packet in the same time slot to be collided will be higher. So that increase. So again, that's a difficult to determine the optimum number of retransmission in order to get the best performance in terms of the lowest probability of fail. The figure on the right is to show different number of retransmission with different data rates, so you can see the same phenomena. Okay, so the next technique is called the random linear network coding. So the random linear network coding basically is to make use of this Galois field with this coefficient with the packet sent by different node or transmitter. Okay, so what I want to explain this figure on here is that we have R1 node 1, we have R2 node 2. The purpose is that node 1 want to send the packet PA to the destination D1. At the same time, R1 want to send this packet PA to another destination D2 as well. Similarly, R2 want to send a packet PB to D2, and R2 also want to send the packet to D1 as well. Okay, look at this diagram. Since they are very far from, since they want to send the packet, to each other. So if they really want to send this, basically R1 will not be able to send the packet to D2 because they're very far. So in that case, they may need to rely on what we call the relay node to help. Okay, so the question is, if without random linear network coding, just using the normal transmission, how many time slots that R1, R2 need to send the packet PA, PB to D1 and D2? The answer is 4. Okay, why do I say that? Okay, first, since R1 and D2 are very far, right? So first, R1 will send the packet PA, right, to D1. And because the packet is sent broadcasting the packet, so that packet PA will be also received by R3, because R3 is the one that the relay node to help to relay the packet to D2. So that using one time slot. And now R3 receive PA. Similarly, R2 want to send a packet to both D1, D2. So R2 will send a packet PB. So that PB will be received by D2. At the same time, the packet PB will be received by R2. So now two time slot are used. So D1 receive PA, D2 receive PB. Okay, so now R3 receive two packet PA and PB. So now R2 want to relay these two packets to D1 and D2. So first, R3 will send the packet PA. So that PA will be receiving by both D1 and D2. So now this time slot number 3, D2 will be receiving the packet PA from R3. And the next, R3 will send the packet PB in time slot number 4. Now Once the R3 sent, the D1 will be receiving the packet PA. So without linear network coding, basically, R1, R2, or the network need 4 time slot to send this packet PA, PB to both D1, D2. Okay, so now we try to use network coding. What to do network coding is that we can reduce the number of time slot from 4 to 3. So first, R1 send a packet PA. So D1 receive PA, R3 also receive PA. Same, in time slot number 2, R2 will be also sending the packet PB. So D2 receive PB and R3 receive PB. So now, after time slot number 2, R3 receive PA and PB. Now, the R3 will be using the random linear network coding using the alpha beta coefficient of that Galois list field in order to combine these 2 packets together become 1 packet we call alpha PA plus beta PB. At that time, R3 will be sending this single packet only using time slot number 3 to both D1 and D2. And when they receive, D1, D2 will be able to extract this packet to become PB at D1 and PA at D2. Okay, that may be a bit abstract to you. How come we are able to reduce the transmission from 4 to 3 time slot? So let me show you one simple example. So one simple example, not using this complicated Galois list field, we're using XOR. I hope that many of you understand the operation of XOR, right? So show you an example. R1 and R2 want to send a packet with 6 digits, right? 1010 or something like this. Okay, so first, R1 using time slot number 1 to send the packet, all right? So this packet 101010 will be arriving at D1, that's fine. And the packet will be also arriving at the relay number 3, 101010. And in the time slot number 2, R2 will send another packet, let's say 110000 to D2, fine, D2 receive this one. Also, that packet will be received by R3. Okay, so now after time slot number 2, R3 received 2 packets, 101010 and 11000. Now, R3 want to combine these 2 packets using XOR. Okay, hopefully you can recall how we do the XOR of these 2. If you do the XOR of these 2 packets, you will get 011010. So after XOR PA, XOR PB, the packet become 011010. So now the R3 will be using time slot number 3 to send this XOR packet to both D1 and D2. So when the D1 receive this XOR packet, right? Originally D1 received PA. Now, after at time slot number 3, D1 received PA XOR PB. So now I XOR all of them based on the mathematical operation. D1 will get PA. Similarly, D2 originally received PB. Now, D2 received the XOR packet PA XOR PB. So after that XOR operation, D2 received PA. So now, after time slot number 3, D1 received PA and PB. Similarly, D2 received PA and PB. So that's a very important simple concept to understand this linear network coding. In fact, this network coding has been around over almost 20 years already, since the 2000. So the last 5 to 10 years is a very popular to be used in the wireless communication or into the network, wireless network. Okay, hopefully that will give you some good knowledge of this network coding. Okay, so for sure, by using this network coding, you can reduce the number of transmission. For example, I show you from 4 to 3, that can increase the capacity. So that's why for this study, if you're using the network coding, let's say the red line, you can reduce the failure probability substantially for those without network coding in the blue line. Okay. And then the last one I'd like to introduce is called the enhancement of the network coding. It's called physical layer network coding, called PNC. That one also has quite a long history. That one was introduced in about 2006 and 7, so almost over 10 years already. Similarly, last 10 years, 5 to 10 years is very popular technique to improve the network performance. So this, I mean, the one for the network coding, try to combine the packet from the digital digital base 1010. This one try to combine both packet from the analog signal. So that one even more complicated. So I'm not going to introduce here to you. But what I want to say is that this PNC will be able to reduce the number of transmission from 4 to 2 time slot, even much better. So how is this like that? Similarly, laptop 1, laptop 2 want to send packet to each other. Without PNC, they need 4 time slot to complete the transmission to each other. But with the PNC, you only need 2 time slot. How does this work? So the idea is that under PNC, laptop 1 and laptop 2 can send the packet at the same time, PA and PB, to the relay node. If you remember, for the network coding, R1 and R2 need to send the packet in different time slot. But under PNC, both laptop can send the packet using the same time slot. And then they can combine based on the analog, the waveform to combine, superimpose their signal waveform. Anyway, the detail, you can see how can they do that. So once they combine these two packet using the analog signal based on the analog waveform, then the relay will combine them and send the combined PNC packet using second time slot. After that, both laptop 1, laptop 2 will be extract the other side packet using 2 time slot. So that is very efficient, almost can maximum can reduce the number of time slot twice. Okay, so that's a PNC. So many studies have make use of PNC for the vehicular network. For the PNC applied MAC layer, the idea is that they use one of the let's say car as in the middle as a relay car. So both car on both sides will be sending the packet to the at the same time to the relay, and the relay using PNC to combine them and broadcast the combined PNC packet to both sides. So both sides will be able to receive the packet from each other. In particular, to send this basic safety message, BSM. Okay. So now to our scheme. So a study which proposed a novel MAC protocol for safety message broadcasting. We try to combine both PNC and random linear network coding together. So the aim of this technique is to disseminate BSM packet using this roadside unit under vehicular network. So each vehicle is expected to have this OBU, and then they can transmit and receive the BSM message. So the transmission range for the roadside unit and OBU is R and small r. Normally, the transmission range of the roadside unit will be larger than the transmission range of the OBU. So in order to execute our protocol, we need some extra decoder at the physical layer for the roadside unit. We need to add the multi-user detector as well as the PNC decoder at the roadside unit. Okay, so we try to study our MAC protocol in these two traffic scenarios. One is a one-way highway. So as you hopefully can see that we try to install the roadside unit, let's say in the middle of this highway, and then with both sides, the car going to the left and going to the right, and then the vehicle have a certain transmission range. We also try to study this idea under this intersection. So I mean, that's a typical intersection. The car goes straight, turn left, turn right. So in the middle of that intersection, we deploy this roadside unit. Okay, so how does this work? So that is the whole idea of the proposed MAC protocol. So for this one, we have divided into 3 different sections. The first one we call the mat setup. If you recall, AU2.11p is using OFDM, right? If you understand OFDM, basically that will be sending based on the symbol. So the OFDM will have the time domain on the horizontal and the frequency domain in the vertical. Each of the box under the mat setup, you can consider one of these resource block under OFDM, the resource block. So what is that in the mat setup, for the car, both sides of the car in the highway or all the car in the intersection, if they want to send the BSM message, the safety message, they need to send a request message, we call the joint packet, into one of these box. Okay, so just by random, the time and also the so there's so many boxes here, so they can choose one of them based on the time and the frequency to send what we call the joint packet. That means the intention to send the BSM message under the PNC session. So after that, for those who are successfully send the joint packet in this one of these resource block or the box, then the central network will do the coordination later to tell them when they can send their BSM message. But however, as I mentioned, the car who want to send the BSM message, they will select randomly one of the box. So there's still some possibility 2 cars will try to select the same box to send the joint packet message. In that case, what happened? Collision. So for the car who have the collision that not able to send the joint packet into one of these box because of the collision, then they will be informed. Then in that case, they can go to the second session, which is the CSMA session. The CSMA stands for Carrier Sensing Multiple Access. That is typically like the Wi-Fi CSMA, that they can randomly send their BSM message under this one. So at least they have some chances to send, but there's a possibility if they send the packet, BSM packet under the CSMA, there's a chance that the packet will be corrupted due to collision. But at least we give some opportunity for them to send under the CSMA session. Okay, so now we go to the last session, the PNC session. So for those cars who can successfully send the joint packet under the mat setup, right? That means they can send the joint packet into one of the box under the mat setup. They will be informed under the PNC session that they allow to send the packet at what time. So look at the BNC, the physical layer network coding session. So those 2 cars, let's say, under this highway, right? Maybe V4 and V3, they allow to send the BSM message under this PNC session. In that case, under the PNC session, they will be informed when to send. So in that case, V4 and V3 will send the safety message at the same time to the roadside unit. So that's what I mean. So let's say V3 and V4 allow to send the BSM message 1 and 2 at the same time to the roadside unit. So once these 2 packets received at the roadside unit, if you remember for the PNC, then the roadside unit will combine them together. And then after that, the roadside unit for the second box will try to broadcast the combined BSM 1 and BSM 2 message in the downlink. Okay, remember, vehicles send the BSM message to the roadside unit using the uplink. Then after these 2 messages arrive at the roadside unit, then the roadside unit will combine them using the PNC and then send this combined one using the downlink. So as I record this, right? Laptop 1, laptop 2 send the message at the same time to the relay, and then the relay will combine them using PNC, and the combined PNC packet will be sent to them in the downlink at the same time. Okay, hopefully you can associate this diagram to the PNC operation, okay, etc. So after a number of cars who are allowed to send under the PNC, we also allow some relay. What I mean is that, so for example here, right, when the V4 receive the combined message from RS, so the V4 receive the packet from V5 based on PNC. But however, you look at the highway, some other car may be far from the roadside unit. So in that case, V4 will try to send this as a relay to send this packet broadcasting to other car using random linear network coding to enhance the packet reception. Okay, so that is the later part. Okay, so basically that is the description of a MAC protocol. Try to combine both PNC and random linear network coding, RLNC. Okay. So this is the word description. So I will not go through just like what I described to you. Okay, so this is our design. So now we like to look at the performance. We study our protocol using the NS3. These are the typical parameter we're using: the data rate, the packet size, the speed of the car, and the channel is under Nakagami fading. Okay, first of all, that's very important, right? Because you can see our protocol is what I mean, kind of very complex, you know, combine 3 different sessions: MAC setup, CSMA session, and the PNC session. And then under the safety message transmission, the time is very critical. And then we need to see whether we can meet the time requirement. So the time requirement is that the safety message need to be sent and received by the car less than 100 milliseconds. So there's a different combination of the session. For example, that one, the black one is the PNC, the red one is the CSMA, and the blue one is the MAC. So each of these combine the transmission time of these 3 sessions. As you can see, for the roadway scenario, intersection scenario, the combination of the transmission time of this 3 sessions is still less than 100 milliseconds. So that means even though for 160 car on the highway for that scenario, so that means our protocol still acceptable according to the standard that to send safety message within 100 milliseconds. Okay, we look at the performance, the packet delivery ratio. So the one on the left and right is a roadway and intersection with different at the data rate of 6 megabit per second. So look at the graph on the left. The red one is the AU2.11p protocol, the standard one under DSRC standard. And the blue one is only using the network coding. So you can see the red and blue, the packet delivery ratio with the number of different cars actually is quite low, less than 60%. What does it mean? That means only 50% of the chance the car can receive the safety message from other car. Actually, that's quite bad. So we also try to implement other research technique, which is the network coding and the our PNC, the ping line, only network coding relay, only network coding, which is the ping line. So with the network coding relay, the performance improve. But however, when you have many cars, the packet delivery ratio also quite poor, less than 40.4. Okay, so now look at our scheme. Our proposed scheme substantially increase the packet delivery ratio. We can maintain very high, over 90%. Even though we have 160 cars in the highway, we still can have the receiving probability over 70%. Okay, so now we try to study our proposed scheme with different data rate. So we try to look at data rate 3, 6, and 12, 27 megabit per second. So no choice. For the low data rate, we still can perform quite well, even though for 12 megabit per second. But if you have high data rate, then the packet delivery ratio is still very low. So that is something that we need to address, because high data rate mean much more packet will be sent by many other car under this BSM. Okay, so we try to study a different ratio. If you the one I show you is that the transmission range of the row, I mean of the OBU is 1/3 of the RSU. What I mean is this. So that's a transmission range. The transmission range of the OBU, that means the transmission range from the car is only 1/3 of the transmission range of the roadside unit. So that is what I do for the study I show you. And now we try to increase the transmission range of the vehicle. So increase to 2/3. As you can see, if you're increasing the transmission range of the vehicle, the data rate increase. Okay, but however, that is only for the BSM. But if you allow the car to transmit for other type of packet, the situation may not be the same. So even though we increase the transmission of the vehicle, we can increase the packet delivery ratio. But however, we still need to further study whether that will really benefit the whole performance. Okay, so now we try to use more relay. As I mentioned, the previous study, we rely on the single relay. So for example, the V4 we use as a relay to send the message to the V6 using random linear coding. But in this study, we try to increase one more. Let's say for the V5 here is far from the V4, so that the V4 may not be able to reach V5. So now we try to increase one more relay, V6. So when the V6 receive a packet from V4, V6 will try to relay this packet to V5. So we try to use two relay, what we call the multi-relay scheme. For sure, when you're using more than one relay, you can improve the performance. So the black is a single relay, and if you compare with the blue one, is using two relay. So you can see if you are increasing to use multi-relay, the packet delivery ratio can be increased substantially. So that is the scenario. But however, the system will be more complex, and somehow that may create other issues as well. Okay, so I think that would be my last slide. So in this study, we try to propose a hybrid MET protocol, and that can effectively suppress the transmission condition for the safety message transmission under WANET. So our proposed scheme consists of both distributed CSMA session as well as the centralized session, the MET setup, and the PNC session. So we try to integrate both PNC and random linear coding together to support V2V and V2I communication. And our study find that actually the communication complexity is only linear increase with the number of car. So it's still quite feasible in terms of the complexity, and that is compatible with the DSLC standard. Yeah, that's all for me. Hopefully it's not too long for the student. Yeah, I welcome for any question.
Thank you so much for such an informative session, sir. I'm sure the students have gathered a lot out of it. In fact, before I throw the round open to the audience, I have some questions from my colleagues, right, sir? So a bunch of questions came over to me, and I'm trying to put across, if you allow me to. So one of our, members here was curious to ask you, how does joint physical layer network coding differ from the traditional network coding?
Yeah, okay.
Throw some light on that.
Yeah, there's a very technical one. Okay, so I think you can understand how we do the network coding from the digital, right? Okay, are you able to see my screen? Or I
So we are able to see your screen.
Okay, good, yeah. Okay,
The
so
screen,
I
are you
think
trying to show us some slides, sir?
yeah, are you able to see my slide now?
The slide is yet to be visible. I'm sorry.
can you see this slide about the RLNC? Are you able to see?
You have to share your slides. Please
So
share
right.
slides, sir.
Okay, let me see if I can share. Okay, I think I may need to share again. Oh, I share already, right?
Yes, sir. You need to share again.
Okay, let me share again. Yeah, okay. Okay, good. Can you see my
Yes,
slide?
getting shared, sir. We can see the slide now,
Okay.
sir.
Okay, good. Okay, so I think that is easy to understand. The network coding from the digital bit, right? Basically, it's an XOR. Okay, but the network coding from the physical layer actually is very, it's very smart one. What they do is that they try, okay, just for example, using the BPSK, all right, BPSK waveform, right? We have the up and bottom part, correct? We have the up and bottom part. What they do, they try to combine two digital bit using the waveform. That means if the both waveform, right, let's say is the positive, if both waveform are positive, they will add together and become positive. And if they both is negative, this waveform will add together become more negative. So that would be the, and then if the positive and negative add together would become nothing, right? Because of the waveform, if you recall the the sine and cosine waveform for BPSK. So based on this kind of combination, positive waveform become more positive, negative waveform become more negative, and positive negative become nothing. Then based on this one, they can have a table to decode this one. So at the end, they're able to recover the original packet. So that is very smart in the way that they are able to reduce the transmission that allow laptop 1, laptop 2 to send the waveform at the same time, and they can combine the waveform at the same time. They have to be synchronized. And if you have followed this PNC, the inventor of this one actually is from Chinese University of Hong Kong. He's my good friend, is a Professor Sean Liu. And he's the one that to discover this technique, yeah, from Chinese University of Hong Kong. And in fact, the network coding was also invented by the same universities, actually same group of people. If you know the name, one of them is called Professor Raymond Yang. You're also from Chinese, the same department, the same university. So that's very great. Both of them are the colleague that one of them invented network coding, the other one invented physical layer network coding. I'm sorry I'm not able to explain too detailed because actually it's a quite complicated idea for the PNC, but working quite well.
Absolutely, sir, but very well explained for our audience of the day. So, one more question from our end. What are the main challenges or limitations with implementing joint physical layer network coding based MAC protocols?
I mean, very challenging. I mean, honestly, this is to me is difficult to implement because so complicated. But I mean for research is good. For implementation, because for this one, a lot of things. One of the very important is the synchronization, because you really need the synchronization from the car. So if you especially have so many car, the synchronization will be lost. And second, when we implement this one, because of the speed, right, car will be come in and coming out, will be keep moving. So some of them may not be able to work well, but I mean, still can, that one, I mean, one is the difficulty to implement because it be complex. Even though you implement, the performance definitely will be worse than what I show you from the simulation. But I believe that there's still some improvement, but I will not have a high expectation of very good improvement. But anyway, this is some idea, but further study need to be improved to simplify in order to get performance for those more practical to be implemented. Yeah.
Great, sir. Thank you so much, sir. One more question from Amity University, Tashkent candidates. How does, how does the entire setup describe the practical applications where JPNC based MAC protocols would be beneficial for applying and using, gaining the utility?
Yeah. Okay. As I mentioned, I mean that one is something that can be implemented. So one of the way I think if okay, I mean that can still be implemented to benefit. I mean the transportation for not too fast transmission. I mean, not fast driving. So if the highway or whatever, I mean, for the city environment, let's say the limit up to 50 km/h, that I think still can feasible to be used for this one, because as I mentioned, the car will be coming into the coverage of the roadside unit and then leaving.
As
If
you
the
showed
speed,
in your example, sir, just as you showed in your example.
yes, yeah. So that's one will be implement to benefit for the traffic. Yeah.
Perfect. Sir, how does JPNC affect the latency of wireless communication systems? Would you comment on that for the audience, sir?
Okay, yeah. I mean, okay. Yeah. I mean, for sure there's some delay. That's why I show the. So we need to show. I mean, the latency at the end is to show how is that the message can be received. That's why this graph is somehow to support the transmission delay. So I mean, you can see all the session together. Even though with over 160 car, we still can complete the transmission over this three section. Let's say the MET setup, CSMA, PNN session, less than 100 milliseconds. So that means for sure there's some delay, but however, we still can manage to meet the standard. The standard means that you have to send the safety message within 100 milliseconds. Yeah, they still marginally can meet the requirement. Yeah.
Great. Sir, now I would want the audience here, the young audience, our students to put across questions directly.
Yeah,
Can
sure.
we hand over the mic to the student who wants to put a question? Please introduce yourself, name your batch and your program, and you may put across your question to the guest.
Good afternoon, sir. Am I
Hi.
audible? My name is Ibrahim Koja, and I am from BTech CSE, second semester student. And I had one question about, you have shown us theoretical analysis. Is there any real life implementation of GPLNC?
No. Yeah, I mean, for sure. I mean, this is still on the research stage, because I mean, for this kind of work, I mean, the many of the proposal has been proposed. So this is one of them. Try to make the improvement. But right now, the current one still using the basic one, 11P. So that's still not. I mean, for the implementation, because in terms of implementation, that need to go to the standard. I mean, that need to be adopted, by this major player. Yeah. So that one, I mean, still on the research that to show, but hopefully that kind of idea will be able to influence some of the major player, to be considered to be implemented. Yeah. No, that one still has not been implemented. Only can show you some, as you mentioned, theoretical result based on the simulation. Yeah.
Sure. And I also had one question. What are the mechanisms to ensure security? Because these messages can be easily, how to say?
Yeah, to steal the message, right? Because you have to send this message to other car to help you to do the relay, correct?
Yes,
Yeah.
I mean, those messages can be easily changed, and
Yes.
there could be cause traffic jams and traffic accidents because of those messages.
Yes. Yeah, for sure. This kind of thing, I mean, definitely it can be easily to be altered, right? To change. So, but however, I mean, this is not the focus. For sure, there are many other wireless network, I mean, the security protocol to be used. So that one need to be used together in order to ensure that the message has not been changed. One of the actually is very hot topic right now. Also, some of I like to do in the past is actually the blockchain, right? As you know, blockchain is the technique that to ensure that the message has not been altered to be the legal message. So that part, I mean, blockchain can help. At the same time, all other security kind of the security protocol can be used as well on top of this one. But for this one, then for sure we do not consider, assuming that the security has been taken care well already by the network. We only purely look at the capacity, the throughput of this system. Yeah, the network performance. Yeah.
Thank you, sir.
Thank you
Thank you.
so much. Who's the next candidate from the audience? Sir, in fact, to be honest to you, there is a lot of curiosity among the audience here. However, because of the shortage of time, we would request the audience to bear with us and move ahead with the schedule. We are highly
Understand.
grateful to you, sir, for your presence once again, and to expect our gratitude. We, in the form of a small token of love, appreciation, and respect from Amity University Tashkent family, we present to you a certificate of appreciation from our end, sir. Kindly accept it. The soft copy of the same will be mailed to you by Dr. Sudhanshu, sir.
Thank you very much. Thank you very much.
I request the IT team to display the certificate. Thank you so much, sir, for your time, your precious time, and the informative session you presented to us today. And without much ado, I close the session, thanking everyone involved in it. We look forward to many more of such kinds in times ahead. And I welcome our guests for the next session. A very warm welcome to ma'am and the dignitaries on the dais. Thank you.
Thank you. Thank you. Thank you. Bye-bye.
Over to Dr. Shalki for now.
Good morning, everyone. Ladies and gentlemen, distinguished dignitaries, faculty members, students. A very good morning, everyone. It is with immense pleasure and pride that we gather here today, where this momentous occasion marks a significant milestone